All right, so this will be our last one, even though I want to do applications of economics bad, but I'm gonna stay away from the applications of economics. Maybe I'll make another video and pop it in here at a later date. But most of y'all are not econ majors. Most econ majors typically only go till math 30, which makes no sense to me. You need calc 3 for econ, but hey, now I'm just babbling. Let's go. Last one. Wait a second. Theorem 6.3. It's net change. I feel like these are all the same things. Remember the velocity and position, the acceleration and the velocity, and now net changes? They're all the same thing. There's no difference. It's just all about what application you're putting in there. So suppose a quantity Q changes over time at a known rate of Q prime. So we have a quantity Q, and Q prime is the change in the quantity. Then the net change in Q between time equals A and time equals B, where B is bigger than A, of course. Just take an integral of the rate of change, and you get your net change. Now our second part, so given the initial value of the quantity at time 0, the future value, or how much you're going to have after time greater than 0, is whatever your initial value is, however much of it you had, plus the integral of the change in the quantity from 0 up to t. So let's try a problem. Cell growth. So this is for you bio majors out there. I don't know why you're taking this class for your bio unless you want to go to, I don't know, maybe you're just a nerd. I don't know. Different schools, different prereqs. All right, so cell growth. A culture of cells in a lab has a population of 100 cells when nutrients are added at time t equals 0. Wait a second. That means Q of 0 is equal to 100 cells. So its initial value was 100 cells. You need that. Oops. Can't call it Q. They're using N. Sorry about that. Again, another example straight from your text, so you can go and look at it again if you'd like to. So when nutrients are added at a time t equals 0. So suppose the population, N of t, in cells per hour increases at a rate given by 90 times e to the negative 0.1 t. Okay. Now we want to find a function. So let's set it up. We're like, all right, so n of t is just going to be equal to our n of 0, our initial value, plus the integral from 0 up to, how do we do this again? Oh, t. We're going to put in a t right here. What do we do here? But now I have to change these variables. I gotta change these variables out. Notice how they use the x. I've been staying away from this for a bit. Q prime of x. We need a dummy variable here. All right, so we're going to just mess with a dummy variable. I'm going to call this instead. I'm going to say that this is 90 e to the 0.1. Oh, no, not t. I'm sorry. I'm sorry about that. X dx. And you're like, what? Yeah, we need a different variable. We're trying to just create something here. So let's go. So our n of 0 was 100. We replace this with 100. And now let's find the antiderivative. Now I'm going to jump through this a little bit and call this 90 over 0.1 e to the negative 0.1 x evaluated from 0 to t. I'll let you figure out how that quick-ass use of is done. I swore again. Gosh, I gotta stop swearing. All right, so it's 100. Now I just want to change this. That's going to be negative 900 e to the, this sucks. All right, now let's do it. Dividing by a tenth is the same as multiplying by 10. I don't like decimals. But I know you're going to see them, so I want to make certain that I do them as well. So, Okay, now we put it in. We're like negative 900 e to the negative 0.1. And we got to put in our upper bound first. But that's just t. It's just a t. Okay. Cool. Minus negative 900 e to the 0th. But that's anything raised to the 0th power other than 0 is equal to 1. So what do we have? We have 100 minus 900 e to the 0.1 t negative plus 900. So it turns out 100 times plus 900 is 1,000. And here we go, my friends. There's our function. So what we're learning here is that we can, at any time, if we know the rate of change of something, it doesn't matter whether it's velocity. Velocity is the rate of change of your position function. Acceleration is the rate of change of your velocity function. Jerk is the rate of change of your acceleration function. Maybe it's going to be cells in a petri dish. Maybe it's going to be marginal cost, as it has to do with economics. They're all the same thing. Our net change is, if you can tell us what the known rate of change is, and you can find the antiderivative over a time interval, we're just using the fundamental theorem of calculus part 2 to find out that net change. Also, to find a future value, as long as we know the initial value at the beginning, we can just add it to the integral from 0 up to any time t with respect to dealing with its rate of change function. So you wanted to take calculus, huh? Okay, you probably didn't want to. You wanted to be a STEM major. Fun stuff. All right, that's it. Next section, you won't dislike it as much. I like this next one. Pretty good. Areas between curves. I'll see you.